Questions, problems, Hawk stuff, review problems. What have you guys got? So this is like a open office hours, right? Let's see. I'm just going to start calling on random people and see if they have any questions. Chastity, do you have any questions from Hawks or those review problems I just wrote down, or anything from the videos and the videos I've uploaded so far? Okay. Isaac, do you have any questions?
Not any currently.
Okay. Let's see, who else? Alexandra? Oh, okay. Yes, Stephen, go ahead.
Can you hear me?
Yep.
On 7.2.
Yeah.
The first exercise you started doing, with the four-digit pin number.
Oh, in the video,
like
yes.
In the video, yeah. When you were writing down the diagram,
yeah,
you actually included 10.
Ha.
Is that right or wrong?
No, it should be 0 through 9.
Okay, all right. I just wanted to make sure and clarify.
Yeah, dang it.
That's okay. It just kind of stuck out to me because we kept saying 10 of everything, and then I was like, well, zeros kind of.
Yeah. So did I write 0 through 10, or did I write 1 through 10?
Yeah, you wrote 0 through 10.
Oh, so I wrote 11 things. Yeah. 10 is not a digit. 10 is not a digit.
Gotcha. Right.
Yeah.
Okay. All right. Thank you.
Yep. No, I'm glad you asked, because I hope I didn't confuse anyone else on that. Okay. Let's see what else. So, if you guys don't have any questions, I'm going to work through some problems from that review set I just gave you. Now, keep in mind, if you're working those review problems that I wrote down, you may not be able to do some of the ones from 7.2 and definitely not 7.3 yet, because we haven't covered them. I'm just giving them all to you at once, so you can just have them for reference. All right, so let's do 7.1, number 4, in the text. So it's a long problem. I'm not going to write it all out. You can, if you don't have your ebook pulled up right now, you can pull it up later if you want to, or actually really, like, the best thing would be just to have it open now. Okay, when choosing an outfit, you have a choice of 3 shirts, white, black, or patterned, a choice of 2 jeans, faded or dark wash, and a choice of 4 pairs of shoes, sandals, running shoes, climbing boots, or mules. List the sample space in regard to the outfits, combinations of shirts, jeans, and shoes you could pick from. So we have 3 choices of shirts. So we have shirts. So they're asking us to write down the sample space, which is like the total number, or well, not number, the total space of things that we could possibly choose from. And why do we care about that? Why do we care about sample space? Because when we're calculating probability is just built from 2 numbers. Like, in the simplest sense, it's a fraction, numerator over denominator. That denominator is the size of the sample space. So knowing what a sample space is very critical for calculating probability. Okay, so we have shoes. Sandals, running shoes, climbing boots. Sandals, running shoes, climbing boots. Okay, and I don't know what a mule is. I guess it's like a shoe or something. Okay, so they also give us, if you're looking at the problem, letters to use to represent each of these. And thank goodness none of these are sharing letter names, so we don't have to decide to name something weird. All right. Okay. So we want to list the sample space, and they say in regards to the outfits that you could pick from, where the outfit, one particular outfit is going to be some combination of shirt, jeans, and shoes, some triple of shirt, jeans, or shoes. Shirt, jeans, and shoes, rather. So I could have like a patterned shirt with faded jeans and sandals, which sounds super fashionable. All right, so we want to list the entire space here. Now, if you've watched the video for 7.2, then you know that there is a way to count up how many total possibilities there should be. Right, and that's by looking at, now they didn't ask for the size, they didn't say find all the possible, like the number of possibilities, but it would be nice to have the number in mind so that we know if we've missed anything when we list them all out. So we know that if you've watched 7.2, that video, that I can draw little horizontal lines, and each of these is displaying like some category, like shirts, jeans, shoes, and I can put the number of choices within each category, right? So if this is shirts, then I have 3 choices here, and I have in jeans 2 choices here, and then 4 choices here. And we proved by a tree diagram, well, I'll say we proved, but we showed by example that what you can do here to find the total number of options is you can just take the product of the number of things in each category. In other words, we should have 24 possibilities, 24 different outfits, 24 unique possibilities. Now, what they really want here, though, is they want us to list them all out. So all I've done here is just find the number that we're aiming for, which can be helpful so that we don't miss anything. All right, so how would you actually list this out? Like, how would you stay organized? Well, you got to have some kind of, probably some plan in mind so that you make sure you don't miss anything. I would say that I would pick a shirt, right? Pick a shirt color and then a jeans color and then get all the shoes, right? So like white shirt, faded jeans, and then all the different, so that'll be 4, right? And then white shirt, dark wash jeans, and then all 4 shoes. And then I'd move on to the next colored shirt and do the same. So that's how I'm going to list this here. I'm going to say, first of all, sample space is a set. That's why I'm writing it with curly brackets. All right, so W for white shirt and then faded jeans. That's going to be my first like anchor point. Okay, and then I'm going to have sandals. And then I'm going to have white shirt, faded jeans, running shoes. White shirt, faded jeans, boots, or climbing boots. White shirt, faded jeans, mules, comma. Okay, now I'm going to move on to black shirt. No, not yet, sorry. I'm still on white shirt. Now I need to go to dark wash jeans. See, hopefully you're seeing my process here. This can be really useful when you need to make a giant list. You know, if some sample space is really large, it's helpful to have some plan in mind. Like this, to pin down the shirt and then pin down the jean and then do all the last category. And then keep the shirt pinned down, move on to the next choice in the second category, and then do all of the last category. So now I'm done with white shirts. I've got all the combinations I can do for white shirts. And you may note that there's 8 of them. So I should expect the same number of combinations for black shirts and patterned shirts. So 8 more and 8 more. By the way, 3 8s is 24. So this should be, looks like it's going to work, right? Okay, so now I'm going to move on to black shirt, faded jeans, sandals, black shirt, faded jeans, running shoes, black shirt, faded jeans, climbing boots, black shirt, faded jeans, mules, and then black shirt, dark wash jeans, and just, it starts to get easier as you see the pattern. Oh, dang, I was going to change color. Oh, well. Okay, so there's all the white shirt combinations and all the black shirt combinations, and now I need the pattern shirt combinations. Okay, so I have pattern shirt, faded jeans, sandals, pattern shirt, faded jeans, running shoes, patterned, faded climbing boots, pattern, faded mules, and in fact, I'm not even looking at the list up here anymore. I'm just kind of copying. Whoops. D. That's D for dark wash jeans. Okay, and then close the set with curly brackets. There it is. There's my sample space. There's my sample space for this set. So why did I pick this one as a review problem? Well, because it's really a test of how organized you are, right? It's showing, if I know that you can do this problem, that it tells me you can stay organized when you're dealing with things, when you're dealing with a large sample space. It also shows me that you probably know how to find the size of a sample space. That's not super necessary to do for this problem, but it's really nice to know so that you know if you've done the right number of items. Okay. Any questions about that one? So the next little chunk of problems is about determining whether each probability is empirical or classical. Those are all right. I mean, I didn't assign any of those as extra practice because, I don't know, I just don't find them to be that important. I mean, it's nice to know whether something is an empirical probability or classical. And I gave you an example in one of the videos of an empirical probability. So the point is, the thing to know is that classical probability is like a theoretical probability that you calculate with math. And empirical probability comes from doing experiments. And there is such a thing called the law of large numbers in probability theory that says that as you do more experiments, your empirical probability should look exactly or very much the same as your classical probability. And as you let the number of experiments approach infinity, which makes no sense in the real world, but if you did on paper, then the theory says that the empirical and classical probability should perfectly match. And we actually saw that in that experiment I did with the rolling of the dice, or rolling of the die rather, and saw that those two probabilities were really close. All right, then what do we have next? So the next chunk of problems is about calculating empirical probability. So what they do is they've run a bunch of experiments already for you in numbers 9 through 12. I didn't assign any there. I'm more interested in classical probability. So the next one I assigned is number 13. So 7.113. It says the instructions for the problems are use classical probability to calculate each probability. Assume individual outcomes are equally likely. Of course, that's been the underlying assumption for this entire chapter, really. And round your answer to the nearest millionth if necessary. Okay, so yeah, when they say assume individual outcomes are equally likely, what they're saying there is if things are not equally likely, then you've got to adjust your math and things get a little bit more complicated. So we are assuming all the experiments, the events are equally likely. Find the probability of obtaining exactly one head when flipping 4 coins. Okay, so first thing to do is to list the sample space, just like this last problem where you had all the shirts, jeans, and shoes. We need to find the size of our sample space. Well, so do we need to list it all out explicitly? No, but it's a good exercise, and we really need to know the size of the sample space as well. So I'll do both just for practice. So let's see. We have, well, let's do it this way. I got my coins here too, I might use as a prop. Okay. Let's find the size of the sample space first. So we're just considering how many different possibilities there are when you flip 4 coins. Well, then that means there are 4 categories, right? There are 4 categories here. How many options does each category have? Anybody know? When I flip a coin, so each one of these little spots is representing a coin flip. So how many options are there for each coin flip?
2.
Yep, 2. That means there are 2 here, 2 here, 2. It's the same for all of them, right? 2 here, 2 here, 2 here, 2 here. And we know by the rule from 7.2, the so-called fundamental counting principle, which I've already used in the last problem, right? We should get 16 possible outcomes. Now, let's list them just so that you believe me. So this is going to be the number that goes in the denominator. Goes in the denominator of my fraction when I calculate my probability. But just in case you don't believe me, let me write them out. So we could have, and I'm going to use H and T to represent heads and tails. So first I could have all heads. See how I stuck? That's one event right there, 4 straight heads. Then I could have, now I need to have a plan here for how I'm going to organize these. I think I'll do it like this, put tails there. And then I could have, whoop, I've already messed it up. T, H, 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 T, H, that's not an F, that's a T. And then I could have H, T, H, H, T, H, H, H. Let's see, then I could have, how do I want to do this? Heads, heads, tails, tails. Probably should have thought about a better way of doing this. Heads, tails, heads, tails. You know what? I don't like this. Let's do it a different way. Let's use a tree diagram because I'm going to get out of whack here. So let's do it like this. Let's say first category we have heads or tails. And then off of each of these, we have heads or tails. This is a so-called tree diagram. This is like one of the ways that we showed that the way to find the number of total possible outcomes doing this little trick up here. This is one way that we showed that it's legitimate to do that. All right, now off of each of these, so this is second category. Now off of each of these, I have 2 choices off of every single one, heads or tails. Oops, heads, tails, tails. And then off of each of these, so this is the final category here, heads, tails, tails, heads, tails. These tree diagrams get pretty messy. You go anywhere beyond like 10. They have a really nice one drawn out in the text at the very front of 7.1. That one's pretty nice to look at. Okay. Now, how do I make a list of all of these possible outcomes? How do I make a list of these? I follow through like this. I go heads, 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 tails, heads, heads, tails, heads. So, oh, by the way, how many are there? If I just count up at the end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Good. All right. So I have the first one, heads, 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 heads. That's this, 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 this. Then I have heads, 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 tails. Then I have, so this one, these 2 are done. Let me cross them off. Those 2 are done. Then heads, heads, tails, heads. Heads, heads, tails, tails. So these 2 are done. And also these are done, right? And that one. Okay. Heads, tails, heads, heads. Heads, tails, heads, tails. Okay, so these are done along with that one, and then heads, tails, tails, heads. You can see this is this becomes quite heads, tails, tails, tails. Quite annoying to write down. Okay, there should be 1, 2, 3, 4, 5, 6, 7, 8. There should be 8 at this point. This is all of the possibilities that begin with a heads. All 8 of these begin with heads, and this is all the possibilities. Now I'm moving on to these that start with heads, or start with tails, sorry, start with tails. So actually what I'm going to do, instead of like trying to follow every single branch through, I'm going to just copy this list up here, but with tails up front. You got to find things like that to make this bearable. Finally, tails, 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 tails. Oh my gosh, got it done. All right, there they are. There they are. Now, our probability is going to be some number, right? Some number over 16 because we have 16 possible outcomes. What is the event supposed to be? What is the event supposed to be? It's supposed to be finding obtaining exactly 1 heads when flipping 4 coins. How many of these options have exactly 1 heads? So this doesn't count because that's 4 heads, right? And 3, 2. So we want the one that just has 1 heads. Or how, let's see. There's more than one, right? There's this one. There's this one. This one. This one. I believe that's it. Okay. So that's 4 out of 16. 4 out of 16. That's the probability. Let me write this down a bit more clearly. You see that when I write down probabilities officially, I have like P and then parentheses. That's where you're supposed to put whatever the event is. So officially, this probability would be P of obtaining. So the event is obtaining exactly 1 heads, or I guess 1 head, should be equal to, well, how many different ways can you get exactly 1 head? Well, we counted that 4. And how many different possibilities are there when you flip 4 coins? Just all together, there's 16. And then, by the way, this can also be written as 0.25, or it can be written as 25%. These are all good answers, though really, if you have 4 over 16, really you should probably simplify the fraction. So you can leave it as a fractional answer, but you should probably simplify it. You can leave it as a decimal answer, or you can leave it as a percentage. All right. The next one I assigned is number 18. Number 18 says, what is the probability that a card drawn randomly from a standard deck of cards will be an ace? So if we have P of drawing an ace, without going through the nightmare that would be writing out this sample space, what would the probability be of drawing an ace? So you're trying to think of 2 numbers, right? You just got to get 2 numbers. What is the sample space size? What is the denominator going to be? How many total possibilities are there when you draw a card from a deck? Anybody know?
Four out of 52.
That's right. There are 52. That's 52, right? 52 total cards. And then, yes, how many? So let me make sure that we know where these numbers are coming from. 52 is the total possibilities because there are 52 cards in a deck. 4 is correct. Yes, 4, because there are 4 aces, right? There are 4 aces. So if you randomly pick a card, you're going to have this probability, 4 out of 52, which is as a decimal. Well, it's some terrible decimal number. Let me get my calculator out. Right, so I'm getting, let's give myself some more room here, 0.076923076923, and it just starts to repeat that whole chunk. That's kind of interesting. I don't know if you knew that, but rational numbers, you know, you've seen like 1/3, right? 1/3 is just a bunch of 3s, or 2/3 is a bunch of 6s. Well, rational numbers can be entire chunks of digits that repeat. So that's pretty interesting. Anyways, that's not that we don't want to get into like number theory or anything here. The book tells us, or the instructions say, round your answer to the nearest millionth. So the millionth, by the way, is going to be, let's see, 10th, 100th, 1000th, 10,000th, 100,000th, millionth. So do we round that 3 up or down? Do we just round everything down and chop all this off? Or do we round the 3 up to a 4? Well, the digit prior to it is a 0, so we round down. Since I'm rounding, I'll say approximately. There we go. And then this, if I wanted it as a percentage, is equal to, remember to get it as a percent, just multiply by 100. In other words, scoot that decimal out 2 places and stick a percent sign on the back. So pretty low chances of pulling an ace randomly, which, you know, like if you know how a deck is structured and how many cards there are and everything, then you have like good intuition. You know that if a card is randomly drawn, then, you know, it's probably not going to be an ace. So what if I wanted to show you this is classical probability, right? Just theoretical, we just thought about what the numbers should be, and that's how we calculated it. But what if I wanted to show you this with empirical probability? Then I would take my deck of cards and I would pull, this would be one experiment. I'd pull a number, okay, and I'd say that's not an ace. I'd make a note of that, and then I'd have to reshuffle it, right? Putting the card back in there, reshuffle it and draw another card, and I just keep doing that until I have a whole bunch of experiments, keeping track of how many aces I have and how many non-aces, and then I would take the number of aces that I got divided by the number of experiments I did, and theoretically, if I did enough experiments, the number would work out to be really close. So I did something like that in the video that you should watch it with I rolled a die, a 12-sided die. I thought about doing the thing with cards, but the thing is, when you do it with cards, you've got to put you draw a card, you got to put it back in and reshuffle them every single time. I didn't want to do that. I didn't want to do that like 30 times. So, though I'd probably get pretty good at shuffling cards if I did. All right. There's a couple more, one more in 7.1. I think I'm going to let you work the last one there. Oh, earlier I said the tree diagram was at the front of 7.1. I meant 7.2. There it is. There's that nice tree diagram for 7.2. Okay, let's see. Now, so 7.2 is when we really started talking about those tree diagrams. But you see the techniques can be used to calculate probabilities. They're helpful. These problems are fun, I think, the problems in 7.2, figuring out how to count things. Let's run a problem together. Let's say, so this is 7.2, and this is just going to be like a problem that I'm making up. How many how many possibilities are there for a 4-digit code? So I'm going to kind of work a similar 4-digit code problem since I messed the one up in the video a little bit. How many possibilities are there for a 4-digit code if we know that it does not begin with a 0 and it ends on a 6? That's interesting. All right. So you've got your boyfriend, girlfriend's phone, and you're trying to unlock it, which is not moral, but this isn't like ethics class, so let's not get into that, right? So you're trying to unlock a phone, and you know that the first digit is not a 0. Somehow you just know that already. And also you've seen them unlocking it, you know the last digit is a 6. And you also do know that it's only 4 digits. Okay. How many possibilities are there? If you got their phone and you wanted to know, like, how many different numbers are there for me to try? Well, what we do, by the way, this is a question. There we go. Draw 4 little lines, 4 little spots here for each of the 4 digits. Each of these is going to represent the number of choices for each place in the code. Not the actual number. This is not an actual code, right? This is going to be number of choices for first digit, right? And the second one will be number of choices for second digit, number of choices for third digit, number of choices for fourth digit. Now, anybody have any ideas how many choices there would be for the first digit?
9.
Yeah, good.
9.
9. That's right. 9. 9, because we know that there are, so why is it 9? Well, we know there are 10 digits to choose from, right? 1, 2, 3, whoops, 0, 1, 2, 3, 4, 5, 6, 7. What is happening to my hand? 7, 8, 9. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. 10 total choices, but we know the first possibility, or the first digit, does not start with a 0, so we only have 9 choices. The next position, the number of digits, or number of choices, is not restricted, right? Number of choices for second digit is just going to be 10, because it's not restricted. It's not restricted. You can have 0 through 9. Third digit, similar. It's still 10. Now, how many choices are there for the last position?
1.
Yes. Just 1, because you know already what it is. So number of choices for last digit. Just a 1. Just a 1. Because you already know what it is. Good, good, good. So now the fundamental counting principle tells us that if we can get this written down, this little diagram thing here, then we just take the product of all of these numbers, and this will give us the total number of possibilities. It's a fun little game to play there, just making up problems like this and coming up with how many different possibilities there are. All right. I worked in example 1 and 2 in 7.2. I worked in the video, and those are really good. They're kind of sort of similar to this, except that they're about passwords that deal with letters and numbers. So that's a really good thing to look at. And then the last thing that I looked at in the video was factorials, which was example 3 in the text. So factorials are going to be like just a special operation in math that deals with products of numbers. So, for instance, if I said, let's see, and again, I'm just making a problem up here. How many ways are there to rearrange the letters in the word math? And I'll capitalize it so we understand that's the word. So how many different ways are there to arrange the letters in the word math? Well, we can start with a similar construction where we have 4 positions, 4 letters here. In the first position, we have 4 choices, M, A, T, or H. But then how many do I have in the second position? Any ideas? It's not 4, right? It should be 3, because once I've picked a letter here, now I only have 3 to choose from. Like if I pick the M, then I only have A, T, or H. Or if I pick the T, then I only have M, A, or H, right? So I only have 3 choices here. And similarly, the next spot would have 2 choices, and the final position would only have 1. This is 4 times 3 times 2 times 1. That's going to be 24 possible rearrangements. All right, so I said I was talking about factorials here. And I am, because this is an example of how a factorial can be directly used to solve a problem. A factorial. Okay, I officially defined it in the video, and there's a nice little definition in the book on page, in section 7.2, page 317. I'm just going to show you what a factorial looks like and show you how to calculate it. So for example, 4 with an exclamation point, and you've probably seen this button on your calculator, though it might look like N with an exclamation point. N just being a placeholder for some number, like the 4. Looks like this, and we calculate it by taking the product of all the numbers lower than it, all the way down to 0, all the integers, all the whole numbers lower than it, all the way down to 1, not including 0, not including 0. So that's 24. Factorials become very useful, not just in like special problems like this that I make up, but in the 2 formulas that you're going to see coming in the 7.2 part 2 lecture on permutations and combinations, which are 2 very interesting ways to count things. They involve factorials. Yes, Jermaine. I just now saw your.
What did you say the 4 exclamation point was? Because I kind of spaced out.
It's called a factorial.
Mm-hmm.
So you would read it as 4 factorial, and this is how you calculate it.
I appreciate it.
Yep. And we'll see that if you read ahead in section 7.2 a bit, there are some formulas, the combinations and permutations, and if you look at that little box that shows you the formulas, they involve lots of factorials, hence why we're not just talking about factorials because I can build problems where you do the same math as a factorial. That's not really the point. The point is that we need to know what factorials are in order to talk about combinations and permutations. Let's see, what did I assign from that? I think maybe the problems I assigned are going to need. Oh, no, here we go. This one's not bad, and we'll probably call it after this, yeah. 7.2, this is number 11 from the problems I gave for review. It says the college's soccer team will play 11 games next fall. Okay. Each game can result in one of 3 outcomes, a win, a loss, or a tie. Find the total possible number of outcomes for the season record. We have 11 games. Each can be a win, loss, or tie. Okay. How do we figure out how many total possible combinations there are? Well, for each individual game, there are 3 possibilities. All right. How can we do this? Well, each category is a game. So I can draw 4, 5, 6, 7, 8, 9, 10, 11 little categories here. Each one is a game. And how many number of possibilities are there for each one of these? Well, 3, right? Win, loss, or tie, win, loss, or tie, win, loss, or tie. Just all of them have 3 possibilities. Now, what does this calculate to? This is not a factorial, right, or anything like this, just a different kind of problem. And what do we end up with here? Well, to say it in a nice compact way, we have 3 raised to the 11th power. If I use my exponent knowledge, right? I know 3 times 3, that, you know, when you're taking a product, a string of products, and it's all the same number, you can compact that with the exponent notation, where this exponent is just the number of times you multiplied 3 by itself. And by the way, what does that calculate to? 177,147. There we go. Either one of these would be an acceptable answer. Now, in real life, it's probably a little bit more complicated because, you know, maybe you I don't know how many games a soccer team will play, but maybe you only get to play 9 games, and if you have a bad enough record, you don't go on to play the last games, or maybe this is like a normal season, and then you go into like the playoffs or whatever. I don't know what it's called in soccer. So real life, always more complicated, but at least we're starting to see how we can model certain things with fairly basic math. You just got like this is just multiplication, right? It's all boiling down to just multiplication. Setting it up, not so easy, but yeah. So that is all I'm going to do so far for 7.2. We'll talk more about 7.2 on Friday. You guys are good to go. Stick around if you have any other last minute questions. I'll see you Friday.